The derivative, instantaneous rate of change, and examples. So far in this section, we've motivated how we arrive at the instantaneous rate of change for a function. Ultimately, our goal is to be able to study functions, see how they change at every point, and use that to find out information about things that we're modeling or studying. One of the key things that we're trying to really understand is something called the derivative. So the derivative of a function is a function in itself. It's a function that tells us how much the original function changed at any given point. So for example, if we knew the derivative of a function and we plugged a number into the derivative, it would tell us how much that original function was changing at that point. And we could plug in whatever number we wanted to. So that's what we're trying to build up to, this derivative function, which will tell us the instantaneous rate of change for every single point of a function. Well, as you can imagine, it's related to the instantaneous rate of change because the derivative of f of x at the point A, which we can write as f prime of A, which you see here, is defined to be the instantaneous rate of change of f of x at the point A. So when we have the instantaneous rate of change at a point, it's also the value of the derivative at that point. So the derivative at a point is the same thing as the instantaneous rate of change. Now, that's also the same thing as the slope of the tangent line. So as you can imagine, there's a lot of ways to talk about the same thing here. So this term, the derivative, is going to become very important to us. And the notation that you see here is something that we'll start to see as we work throughout this class. So again, the derivative is going to tell us how much a function changes at a given point, which is the same as the instantaneous rate of change. Example 1. Use the table below to approximate the instantaneous rate of change of f of t at 1, 2, 3, 4, and 5. So we talked a little bit before about approximating the derivative on a table. And the way that we went about doing that was by looking at the average rate of change to the left and to the right of the point that we were interested in. So since we're looking for the instantaneous rate of change at every single point on this table, we might as well go ahead and calculate the average rates of change so that we can then use them to talk about the instantaneous rate of change. Remember, the average rate of change is going to be f of b minus f of a over b minus a, which is the same thing as the change in y over change in x. So if we wanted to calculate the average rate of change between t equals 1 and t equals 2, we could do the change in y over the change in x. So we would do 16 minus 7, which is 9, divided by 2 minus 1, which is 1. And that would give us an average rate of change of 9. Similarly, if we wanted to find the average rate of change between 2 and 3, we would take 31 minus 16, the change in y, divided by 3 minus 2, which is the change in t, and we would get 15. Moving along, to get the average rate of change between 3 and 4, we would do 52 minus 31 divided by 4 minus 3, which would give us 21. And the average rate of change between 4 and 5 would give us 79 minus 52 divided by 5 minus 4, which is 27. So those are the average rates of change. But in this particular problem, I want the instantaneous rate of change. To get the instantaneous rate of change at 2, I'm going to use the average rate of change on the left and the average rate of change on the right, and I'm going to average those two numbers together. So 9 plus 15 is going to give me 24, divided by 2 is going to give me 12. So my approximation for the instantaneous rate of change at 2 is going to be 12 because I averaged the average rate of change on the left and the average rate of change on the right. Similarly, if I wanted to find the instantaneous rate of change at 3, I would average 15 and 21, which would give me 18. At 4, I would average 21 and 27, and averaging those together would give me 24. Now notice that so far I've deliberately avoided the endpoints because we have to talk about how we work with those since we don't have the option to look at the left and the right. So consider the instantaneous rate of change at 1. So since we don't know what's happening to the left of 1, the most accurate data that we have is what's happening to the right of 1. So we're actually going to use the average rate of change between 1 and 2 to approximate the instantaneous rate of change at 1 because we don't have anything to the left. Similarly, at 5, we're going to use the average rate of change between 4 and 5 because we don't have anything to the right of 5. So that would give me 27. So now I have an approximation for the instantaneous rate of change at every point on my table. But I want to say a little bit about some notation here. So we talked about how the instantaneous rate of change is the same as the derivative at a point. So that means that I could also write some of my information like this. F prime of 1 is approximately 9. So that says the instantaneous rate of change at 1 is approximately 9. I could write F prime of 2 is approximately 12. So that's the notation I would use to talk about the derivative at 2. I could write F prime of 3 is approximately 18. I could write F prime of 4 is approximately 24. And finally, F prime of 5 is approximately 27. So one of the things that we need to get comfortable with is that there's a lot of different ways to ask for the same piece of information. And there's a lot of different ways to write about the same information. So if we're talking about the instantaneous rate of change at 1, that's the same thing as asking for F prime of 1. The word prime represents that apostrophe that's up by the F. And I'm using approximations here because this is a table and I don't have an exact answer. This is my best guess based on what I have. So keeping these terms straight and knowing how to use them interchangeably is going to become something that we need to get really good at. So let's continue looking at examples of how we look for instantaneous rates of change and derivatives on different types of functions. Example 2. Using the graph of f of x below, determine if each of the following derivatives are positive, negative, or 0. One of the things that we want to get really good at is figuring out what the exact derivative is going to be based on a graph. In order to do that, the first thing we want to get good at is being able to envision the tangent line at a point and then using that to figure out if the slope of that line is positive, negative, or 0. So let's start with f prime of negative 2. So negative 2 is over here, and if I go to where the function is at negative 2, I have this point. So I'm imagining the line that touches only at that point. Now my line doesn't have to be perfect for this type of example. I just need to get a sense of where it touches. So here you can see it barely touches my point, but it's close enough for what I need to do. Because I just need to figure out, is the slope of my line positive, negative, or 0? Since my line is going downward from left to right, my line is decreasing there, I can see that the slope of that line is going to be negative. And remember, the derivative, or the instantaneous rate of change, is the slope of the tangent line. So if the slope is negative, that means that the derivative is negative. So I'm going to put a little negative sign next to negative 2. So now, the next one I want to consider is what's happening at negative 1. So at negative 1, I'm considering the point that's here. And again, I'm trying to sketch in the line that touches at just that point. And it doesn't have to be perfect, right? We'll get better at these. And if you have this printed out, you can certainly use a ruler. So I'm trying to determine, is the slope of that line positive, negative, or 0? Since that line is going in the upward direction from left to right, the slope of that line is positive, which means the derivative is positive and the instantaneous rate of change is positive. The next one I'm going to consider is what happens at 0, f prime of 0. So again, I'm going to go to 0. I'm going to go to where that touches the function. And I'm going to sketch in a tangent line. So here's something really interesting happens. The line here looks like it's horizontal. And if your line is horizontal, that means that the slope of the line is 0. So that means in this case, my derivative, or my instantaneous rate of change, is 0. So that's going to happen whenever you have a horizontal tangent line. Now let's go to 1. So again, we're going to go to x equals 1. We're going to go down to where it is on the function. We're going to try to sketch in a tangent line. And we're going to look at whether we think that tangent line has a positive, negative, or 0 slope. Since it's going downward from left to right, the slope of that line is going to be negative. And then finally, we want to figure out what's happening at 2. So at 2, we're going to sketch in a tangent line here. And we're evaluating whether the slope of that line will be positive, negative, or 0. So the slope of that line is upward sloping, and that is going to be positive. Getting really good at determining whether the derivative is positive, negative, or 0 will lay a really solid foundation for the rest of this chapter and for the rest of this course. So if this is something that you're not comfortable with yet, I encourage you to practice this quite a bit, because if you can get this part down really well, it'll really help you in the future. Example 3. Approximate the instantaneous rate of change of f of x equals 4x squared at x equals 3. Or, we could also ask the question is, find f prime of 3. Those questions mean the same thing. So if we're trying to approximate how much this function is changing at 3, what we need to do is we need to find the average rate of change to the left and the average rate of change to the right of 3. And again, the closer we can get to 3, the better our approximation will be. So instead of getting closer and closer, it makes a lot of sense to start really close. So the way I'm going to set this up is I'm going to create my own table. And I'm going to put 3 in the middle. Now, I need to pick something really, really close to 3 on the left and right, and I want to be the same distance away. So I'm going to pick 2.99 and 3.01. So I'm going to go within 1/100th place of 3. That's generally close enough to get a pretty good approximation of whatever you're looking at. So what I need to do now is I need to find the functional values at each of these points by plugging them each into f of x. So when I plug in a 3 into f of x, 3 squared is 9. 9 times 4 is 36. But then I also need to plug in 2.99 and 3.01. So here, when I plug in these numbers, there's going to be a lot of decimals. So I'm going to be really, really careful. When I plug in 3.01, I get 36.2402. I was expecting something fairly close to 36 because this function is continuous and I didn't change the independent variable by that much, so I wasn't expecting the dependent variable to change all that much either. Similarly, if I plug in 2.99, I get 35.7604. So here, I've made the decision to round to 4 decimal places. Generally, that's safe. You always want to keep at least 3 to avoid rounding error. So now that I have the functional values, I need to do the average rate of change to the left and the average rate of change to the right. So when I do the average rate of change to the left, I'm going to do f of 3 minus f of 2.99 divided by 3 minus 2.99. When I carefully plug those decimals into my calculator and I crunch that number, I get 23.96 for my average rate of change to the left. When I do the average rate of change on the right, I'm going to do f of 3.01 minus f of 3 divided by 3.01 minus 3. When I plug that into my calculator, I get 24.02. So my average rate of change on the right is 24.02. So remember, I'm trying to figure out what this is approaching from the left and the right. Now I could average them. However, I feel fairly comfortable saying that these look like they're approaching 24. And again, this is a best guess, so I'm going to use approximation since I'm not entirely sure yet. But I can say the instantaneous rate of change at 3 is approximately 24. So that's how I set these up when I have a function and I want to approximate the rate of change. Let's look at another. Example 4. The population of a small rural town is given by P of t equals 325 times 1.025 to the t. If time t is measured in years since 2010, approximate the rate at which the population is changing in 2012. So here, I need to first figure out what t I'm actually even looking at. So 2012 is 2 years after 2010, which means that I'm trying to figure out what's happening at time equals 2. I could also write the thing that I'm finding as p prime of 2, so the instantaneous rate of change at 2. We're going to approach this similarly to how we did the last one. So again, we need to set up a table where we're looking around 2. There's going to be a lot of decimals here, so I'm going to give myself a lot of space. So I'm going to go ahead and I'm going to use 1.99 and 2.01. Now, you don't have to go to 100th place. You can try the 10th place or the 1000th place, but you want to be close to 2. You don't want to go something like 0 to 2 and 2 to 4. That's too far away. When we say close, we mean things like 1.9 and 2.1, or 1.99, 2.01, 1.999, 2.001. You get the point here. But the thing is, you do get to pick which numbers you choose, so choose them wisely so you don't have to repeat the calculations. So here, I'm going to take each of these values and I'm going to plug it into my population function here, P of t. So when I plug in a 2, I'm going to get 341 point, now there's a lot of decimals here, so I'm going to write them down carefully, 453,125. 453,125. And again, I'm electing to keep a lot of decimals here because exponential functions are a little temperamental. So the more decimals I can keep, the better. That's how many my calculator reported to me, so I wrote them all down. When I plug in 2.01, I get 341.5374491. And when I plug in 1.99, I get 341.3688217. So we have to be a little careful with decimals. We try not to accidentally type in a wrong one, but hopefully you're able to take these and then use them to find the average rate of change on the left and the average rate of change on the right. So when we do the average rate of change on the left, we're going to do the change in y over the change in x, and we're going to get 8.4303. And when we do this on the right, we're going to get 8.4324. So these numbers are really close, which is really, really good. So here, I'm comfortable saying that the approximate rate at which my function is changing is 8.43. So those are the same in both scenarios. So I've rounded because there's so many because they're so close. Now, I want to point out here some of the key wording that was in the problem that told me that I was looking for the instantaneous rate of change. So it says, approximate the rate at which the population is changing. The rate is the instantaneous rate of change. So when you see that word rate, that should send up a signal for you that we're probably finding the derivative, also known as the instantaneous rate of change, at a point. So as you can see, as we move along, there's more and more information that we need to remember on how to interpret these things and apply them. Let's look at one final example here of how we might be able to apply what we know about the instantaneous rate of change to find out further information about a function. Example 5. Suppose we know that for the function below, f of 4 equals 25, and f prime of 4 equals 1.5. Use this information to find the coordinates for points A, B, and C. So here, this one is a little more conceptual. We have to take what we know and see how we can apply it to the situation to try to figure out some stuff that we don't know. So I want you to remember that the derivative, f prime of 4 equals 1.5, is the slope of the tangent line, right? So we know that the slope of this line is 1.5. That's important to us. Now, we also know a point on this line, right? So we know that when x equals 4, y equals 25. That's the point A, right? So we actually already know one of these points. So A is the point 4, 25, right? That's the x, y value. So if we know the slope of a line and we happen to know a point on the line, we can actually use that to get the equation of the line. So remember, the equation of a line is y equals mx plus b. So here we know the slope, which is m, right? So we have y equals 1.5x plus b. And if we want to solve for b, we can use the one point we have, because if you have any point on the line, then you're going to know how to solve for b. So we take our point, 4, 25, and we plug it into the appropriate place. So 25 is the y value, 4 is the x value. So 4 times 1.5 is 6, and we subtract 6 from both sides, and that tells us that b equals 19. So that means that the equation of this line is y equals 1.5x plus 19. So if you're not sure why we would want the equation of that line, think about this. In order to find the points B and C, we already know the x value. So that means if we were to take that x value and plug it into the equation of the line, we would get the corresponding y value, which would give us the point we're looking for, which means that to get that point B, our x value is 4.2, and we're going to take 4.2 and we're going to plug it in for x. So we'll do 1.5 times 4.2 plus 19, and that'll give us 25.3. And that makes sense, right? If you look at the picture, you're expecting the y value to be bigger than the y value at A because it was above A. And here, if we want to find C, we're going to take 3.9, which is the x value at C, and plug it into the equation of the line here for x. And when we plug in a 3.9, we're going to get 24.85. which again makes sense. We're expecting the dependent value at C to be a little bit lower than the dependent value at A. So by finding the equation of that line, we were able to find the coordinates of all the points on that line for various x values. And we were able to get the equation of the line because we knew the slope of the tangent line through the information that we had about the instantaneous rate of change.